Hello dear students. So we will continue our discussion on Chapman theory of layer production. So in the last class we have understood the basic assumptions behind this Chapman's theory. We have also seen how the production rate is a combination of the decreasing number density from the bottom and decreasing intensity of solar radiation from the top. So how we can combine these two, right? So in the last class we have stopped at dx is equals to dh secant chi. Let's call this as equation 1. Okay. So when the solar radiation passes through the atmosphere, a fraction of intensity is absorbed and scattered by the atmosphere, right? Now in continuation what we can see is that so the decrease in intensity of radiation is directly proportional. I mean the decrease, we are talking about the decrease in intensity is directly proportional to, let's say, di, or let's say since it is a decrease, is directly proportional to the intensity of radiation, let's say I, volume of the atmospheric layer, we write it as A times dx, A is the area, and the density of the atmosphere, right? Or we can simply write di is equals to minus A rho I dx. Okay. So from the earlier equation we can replace dh in terms of dx as, so di is equals to minus A rho I dh secant chi. We are using okay. So we know that the density of the atmospheric species varies exponentially as a function of height and the scale height. So we can substitute this into this equation and then we can write di is equals to minus A rho naught I dh secant chi exponential minus h by h. We have just substituted the functional dependence of rho into the di. What is di? Di is the rate at which the intensity decreases from the top. How does it depend? It depends on the area or the volume that it encounters and the density, which is a representative of the number of atoms which are present in that volume, right? And the incident intensity itself, right? So this is just the Beer-Lambert's law, right? So now we have got the rate at which the intensity decreases in terms of angle as well, right? Now let's substitute, let's integrate this equation. Integrating this between I infinity, that is at h is equals to infinity, to a particular height h. Let's do the integration. So integral I infinity to I di over I is equals to integral h is equals to infinity. H is equals to infinity means at the top of the atmosphere, when the radiation is just entering into the atmosphere, where the intensity is maximum, which is being referred to as I infinity, minus A rho naught. Now rho naught is the density at the bottom, that is h is equals to 0, or the surface of the earth, secant chi. Chi is the solar zenith angle, e to the power of minus h by capital H d h. So getting this, we will get ln of I between the limits I infinity to I is equals to minus A rho naught secant chi e to the power of minus h by capital H into minus h from infinity to the height h. Okay, so taking it further, we can write that ln of I by I infinity is equals to minus a rho naught h secant chi e to the power of minus h by h, or we can write I is equals to I infinity times exponential minus a rho naught capital H secant chi into exponential minus h by h. What do you see? You see an exponential outside this bracket, and you also see an exponential inside the bracket. Let's call this equation as 2. What was equation number 1? Equation number 1 was between the oblique height to the vertical height and the angle in between, right? Okay, production rate of ions, let's say, or electrons depends on the solar zenith angle, right? So we are introducing now Q, which is called as the production rate depends on, what does it depend on? It depends on chi, or number of electrons slash ions formed, of course, per unit volume energy absorbed by the atmosphere. And this is called as, let's say, number of electrons per unit volume. We are going to call it as eta. So the production rate, the rate at which electrons or ions are released or produced, depends on the angle at which the radiation is incident, and also the number of electrons and ions formed per unit volume. So this number is referred to as eta. Okay, so we can write Q, which is a function of chi, the solar zenith angle, and the height. That means we are trying to calculate the production rate at a particular height, which is equals to eta times di by dh cos chi. Let's call this as equation 3. Now let's say let's differentiate equation 2. Now equation 2, which is, we will differentiate equation 2 with respect to height and substitute in equation 3. What will we get? Di over dh, the rate at which the intensity decreases with respect to height. I we have already is I infinity exponential minus a, I am just differentiating this, a rho naught h secant chi e to the power of minus h by h exponential x is equals to exponential x times whatever that multiplies x right. So we can get rid of this straightforward. Then we will write di over dh is equals to I infinity a rho naught secant chi upon substitution, simplification, minus h by h minus a rho naught h secant chi e to the power of minus h by h. Right, what is this? This is equation. This is not an equation. Let's say we call this as A. Now, using an intermediate equation, in 3. What is 3? 3 is here. We will get Q, the rate of production, as a function of the angle of incidence or angle of oblique incidence and the height. So, using this expression, we should be able to evaluate the production rate at any height or at every height, okay, which is eta is the number that is produced, A rho naught secant chi cos chi exponential minus h by h minus A rho naught h secant chi exponential minus h by h, which upon simplification this will get cancelled. Eta I infinity A rho naught exponential minus h by capital H minus A rho naught h secant chi e to the power of minus h by capital H. What is this? This is the rate of production as a function of height. As a function of height and the solar zenith angle. Right, now let's talk about, so this is just an expression which is going to be very much relevant ahead. Okay, let's call this expression as A, capital A. Okay, now this is the rate of production for, let's say, for maximum or for peak production. What is peak production? This is the peak production. Let's say if you see this is the peak production at which the rate of the number of electrons are maximum. The number of electrons that are released are maximum, right? So at peak production, we can say that from mathematically you can see that it's the maxima, right? So d by derivative with respect to height of q should be 0, where when q is equals to qm should be 0, or h is equals to hm. Hm is the peak production height, qm is the peak production rate, right? So we take a derivative of this with respect to height, and then we can equate it to be equal to 0, which implies that eta I infinity A rho naught exponential minus hm. So I have substituted h for hm minus A rho naught h secant chi e to the power of minus hm by capital H minus 1 by capital H minus A rho naught h secant chi e to the power of minus hm by h into minus 1 by h is equal to 0. Or we can simplify it, or minus 1 by capital H plus A rho naught secant chi e to the power of minus h by capital H is equals to 0, or e to the power of minus hm by capital H is 1 over A rho naught h secant chi. Let's call this equation as 4. So we can write hm by capital H is equals to ln A rho naught h secant chi, right? Or hm, what is hm? hm is the height of peak production, or where q is equals to qm. That's it. So HM is H times ln of A rho naught H secant chi. So this is valid for any solar zenith angle, any chi. And we can see clearly that the peak production height HM is independent of I infinity, the magnitude of I infinity, right. So if you look back, what we have done so far is we have taken this expression which is just the relation between angle and the length coordinate in oblique as well as in vertical direction. Then we have taken how the intensity drops as it travels. So it drops because we have a minus. I mean, we have a minus because the intensity decreases with respect to height as you are traveling from the top to the bottom, right. So we thought that it will depend on the available density, the volume and the intensity to begin with, right. So there we got the di. Then we integrated this expression for di and we got intensity as a function, intensity at any particular point as a function of the incident intensity after having traveled a distance h in an atmosphere which has a scale height capital H, right. So this is the most important. I mean, if you want to understand really, so this expression tells you how the intensity, what is the intensity when it has been I infinity after it has traveled a distance of small h in an atmosphere with a scale height capital H at an angle chi. That's it, right. So you will realize that it is exponentially decreasing as it travels with, because you have a minus, you will realize that it will exponentially decrease as a function of height from the top, right. This was just about the intensity. Now we introduced the production. So intensity is decreasing. What is happening due to which intensity is decreasing? What is happening? The production is happening. So how does the production depend on intensity? Production depends on the rate at which intensity is decreasing. So more is the rate at which intensity is decreasing, more is the production. So production is directly proportional to the rate at which intensity is decreasing. So that's why you have Q, which is the production rate, and you have a direct proportionality with the rate at which the intensity is decreasing with respect to height. And what else the production will depend on? Production will also depend on how many number of atoms are produced per unit loss of intensity with respect to height. The unit loss of intensity with respect to height is given by di by dh. The number of electrons or ions produced per unit volume is the efficiency, let us say, is eta, and chi is obviously the angle. So the dependence of chi is maintained to just justify the fact that intensity or the production will not be the same if the intensity is traveling and vertically or in oblique direction. So it will be different. So my objective is, so we have already have the intensity as a function of height. So we take a derivative of this and we substitute it into Q. We got the Q expression, which is this. What is this? This expression is the production rate expression, right? Now we wanted, see, this production rate is of course a function of height. So you substitute various different heights. Let's say we start from 450 kilometers and you go up to 0 kilometers. So there are some exponential terms which have guaranteed the decreasing trend with respect to the height, but we also have some terms with the secant, let's say. So due to these two terms, I mean, you won't get a linear way, but so at some point, so this, if you plot this, take random variables and take height, you can take the capital H to be, let's say, 10 kilometers. If you plot this, you will realize that it's not a straight line. It will be a curve. Looks something like this. So we want to see what happens at this height, which is the peak production height. So d, we take a derivative because it is mathematically a maxima. The maxima is the derivative of the function will become 0 at that particular point, at that turning point. So we take a derivative d by dh of q, which is equals to 0. We take the derivative which appears to be lengthy, then upon simplification we will realize that substitute upon making the derivative to be 0 and substituting the height small h to be hm, which is the height of the peak production. Right. So hm is equals to h times ln a rho naught h secant chi. Right. So this is the height of peak production. So hm is, let's write here. Yeah, we already written here. The hm is the height of the peak production. Right. No, so the height of peak production doesn't depend on the incident intensity. Incident intensity was there when we were discussing this, but at some point the height of peak production now is independent of the peak production height. Now let's say from equation 4 we can write that e to the power of hm by capital H is a rho naught h secant chi. Now peak production Qm as a function of the solar zenith angle and the peak production height is eta I infinity a rho naught minus hm by capital H minus a rho naught h secant chi e to the power of minus hm by capital H. We will rearrange this equation for simplification. Qm peak production as a function of chi and hm is equals to eta I infinity a rho naught exponential minus hm by capital H times exponential. So here there is an exponential. So this is what comes here, exponential minus a rho naught h, just a rearrangement. There is nothing that we should worry at this point, hm by capital H. Now Qm using hm, what that we have derived already, as a function of chi and hm is equals to eta I infinity a rho naught 1 by a rho naught h secant chi into exponential minus a rho naught h secant chi into 1 by a rho naught h secant chi. Right. So we have used this. That's it. Okay. So things will get cancelled. This will get cancelled. A rho naught. Okay, and a rho naught h secant chi. Right. So as a result, what you get is Qm chi hm is equals to eta I infinity cos chi divided by h e. So this exponential, this will e to the power of minus 1, which comes here. Right. Now for, let's say, for chi is equals to 0, that means at noon. Okay. So e to the power of minus hm by h is equals to 1 by a rho naught h secant chi, which is 1 by a rho naught h, or e to the power of hm0. hm0 is at chi is equals to 0. Otherwise, it was hm, right? A rho naught h. Let's call this equation as capital B. Okay, now which is Qm at noon at chi is equals to 0. So chi is obviously 0 here, and at what height? At hm0 is eta I infinity cos 0 divided by h e. So which is eta I infinity divided by h e. Right. So what have we got? We have got the peak production at chi is equal to 0 is Qm0 at 0, Hm is eta I infinity divided by He. So let's say this is a very important equation. The peak production at the noon time depends on the I infinity, the scale height. Let's say this is just a number, and eta. So you can write this, rewrite this equation. Eta I infinity is h times exponential into Qm0, which is a function of 0, and Hm. Let's call this equation as C. Using C in A, where do we have A? C is this is C. Where do we have A? Equation capital A. Yeah, this is the equation A. So using this, what are we trying to use? We are trying to substitute for eta I epsilon naught, sorry, eta I infinity in this expression, eta I infinity. What will we get? We get Q, just a production as a function of height, is equals to Qm 0 Hm He that we got from the equation C, then the equation A itself, rho naught exponential minus h by h minus A rho naught h secant chi e to the power of minus h by h. So we will write Q as a function of these two variables. Taking this inside, taking this He inside, exponential 1 minus h by capital H plus Hm by capital H minus secant chi e to the power of minus h by h into e to the power of minus Hm by h, or Q of chi comma h is equals to Qm0 0 Hm into exponential, rearranging these terms, 1 minus h minus Hm by k minus secant chi e to the power of minus h minus Hm, right. Okay, let's call h minus Hm by h. So the normalized height above the peak production height, the height above the peak production height normalized with respect to the scale height. Let's call this as Z. Okay, so then we can write Q, the rate of production as a function of the zenith angle and the height, is Qm0. What is Qm0? Qm0 is the peak production which happens at the noon, right, when chi is 0. 0 and Hm times exponential 1 minus Z minus secant chi e to the power of minus Z. Okay, so this is the expression that we want to derive. What is this expression? This expression, let's see. This expression tells you what is the peak production, what is the production at any given height as a function of production that could happen during the noon or when chi is equal to 0. What does it depend on? It depends on the solar zenith angle, obviously, depends on the solar zenith angle, depends on the height, and depends on the scale height. So this is what, let's call this equation as, let's say, T. Okay, so we've been able to derive using the Chapman's theory, we've been able to derive how the production changes with respect to height. Okay, so there are 4 or 5 major inferences that one can draw based in the atmosphere based on this equation. We will look at that in the next session. Okay. So far we have derived a generalized expression for the production rate as a function of height and as a function of the maximum production. Okay, so we will stop here. We will continue the discussion, which is going to be the inferences on this expression. Okay.